Okay. Hello, everybody. My name is Ahmed Gharbi, and I'm here today with my colleague Sabrine Krichen in order to present a brief introduction to reinforcement learning. We're both engineers or research engineers at InstaDeep. Okay, so the plan for today will be as follows. We will start by introducing InstaDeep. Then we will introduce Google Developers Group. Then we will present an introduction to AI and its applications. And finally, we will dive deep into reinforcement learning. Okay, so InstaDeep is an African AI startup that was founded in 2015 in Tunisia. Now it has 7 offices around the globe and more than 100 employees. So InstaDeep helps its industrial partners to deploy state-of-the-art AI solutions. It offers a wide range of products and a wide range of services, including solving predictions, classification problems, optimization problems, and also decision-making problems. So InstaDeep services allow its partners to unlock data insights to increase efficiency and speed across their organization. And it also helps them to maintain the margins and pricing to stay competitive. So at InstaDeep, we focus mainly on 3 axes. The first one is the research. So there is a lot of research going on at InstaDeep. The second one is the engineering, and the third one is the deployment. Next slide, please.
Hello everyone. So now I'll be presenting the Google Developers Group. The Google Developer Groups are local groups of developers who are specifically interested in Google products and APIs. So each local group is called a GDG chapter and can host a variety of technical activities for the developers. There's also the Women Tech Makers. So Google's Women Tech Makers provide visibility, community, and resources for women in technology. From 2014 to present, Women Tech Makers is continually launching global initiatives to support and to empower women in the industry. So now we'll go with Ahmed. He's going to give us an introduction to artificial intelligence.
Thank you. Okay, so what is artificial intelligence? So AI is the field that tries to make machines perform complex tasks that usually require human intelligence. A few examples for these tasks are learning and problem solving, which are considered very complex tasks. Also, AI can be described as the study of intelligent agents, and an intelligent agent is any device or machine that perceives its environment and takes actions that maximize its chance of successfully achieving its goals. So AI has many subfields. We mentioned natural language processing, speech processing, image processing, and computer vision, and many, many other fields. Okay. So now we will present a brief history of AI. So the first time the word artificial intelligence appeared was in the summer of 1956. Uh, the term was originally proposed by John McCarthy in a summer workshop that was attended by top scientists and mathematicians of that era. In 1969, Cheeky was the first general-purpose mobile robot built. Uh, the other robots of that era needed to be instructed on each individual step in order to complete a task. But Cheeky had the ability to analyze commands and break them down into basic chunks by itself. In 1997, IBM developed Deep Blue, which was the first supercomputer to win a chess match against a reigning world champion under regular time controls. So one fun fact about the match: so Kasparov, the reigning world champion the reigning world champion of that time, accused IBM of cheating later on. In 2002 has seen the invention of the first autonomous robotic vacuum cleaner. It was called Roomba, and Roomba had intelligent programming and had self-drive mode, which allowed the machine to clean autonomously without human control. And from 2005 to 2018, this era had seen the surge of incredible AI inventions like speech recognition, facial recognition. There were some smart dancing robots, smart homes, etc. And so far, the future seems promising for the AI field. Okay, so one might wonder what are the reasons behind the surge in AI breakthroughs? Actually, the success of AI in recent years can be attributed to three main reasons. So the first one is that there are much more data to use and analyze. So almost everything in our lives now is connected to the internet. So you can imagine how much information these devices can generate. The second reason is the advance in computational power. So computers are getting faster and more efficient, and this progress in computational power does not seem to slow down. And the third reason can be attributed to the advances in algorithms and frameworks. So nowadays, there is much more research focused on AI. So naturally, there are new and more robust algorithms every few months. Okay, so when it comes to AI, probably the most popular terms are machine learning and deep learning. So I want to briefly clarify the difference between these two terms. So for example, we want to build an application that detects whether an email is a spam or not. So the way we do this is that we usually have a human in the loop that designs features. He basically extracts the most notable and useful information from a set of emails. And then we use a machine learning algorithm that will have as an input this set of features, and it will learn to classify the emails. Well, in deep learning, the feature extraction step is taken care by the algorithm. So we only have to feed the data to the deep learning algorithm, and it will design by itself the set of features, and then it will perform the classification task. So in a nutshell, deep learning is actually a subfield of machine learning. So another emerging field in AI that seems to have a promising future is reinforcement learning. So what is reinforcement learning? Reinforcement learning is a learning paradigm that is inspired from how humans and animals learn. So scientists assume that humans learn through trial and error from interaction with their environment. And one particularity that distinguishes reinforcement learning is that there is no dataset reinforcement learning. Instead, there is what we call an environment. So, for example, let's consider that we have a robot inside a maze and we want this robot to learn how to escape the maze. So, in this example, we call the robot the agent. The maze is the environment, And our robot can interact with the environment by taking actions. So for example, it can move forward or backward, or maybe it can go to the right or to the left. And every time the robot takes an action, the environment gives back to the agent a state. So a state is basically a description of the environment. In our example, a state can be the coordinates of the robot inside the maze. And in addition to the state, the environment gives back to the agent a reward. A reward is a signal that tells the agent if the actions that were taken are good or bad. So, for example, every time the robot comes closer to getting out of the maze, we can give the robot a positive reward. And if the robot gets away from the exit of the maze, the environment can give to the robot a negative reward. So the goal of the agent would be to find the actions that maximize the received reward. And this type of learning is usually used for decision-making systems. And the reinforcement learning algorithms seems to be very efficient at learning how to play games, but they can be used in many other applications. Okay, now my colleague Sabrine will present to you the some AI applications. I think your mic is muted, Sabrine.
Okay, so can you hear me now?
Yes.
Okay. So thank you, Ahmed, for this avant-goût of reinforcement learning. So later on, we go into the details of the reinforcement learning. But now I'm gonna present you some applications of artificial intelligence. So artificial intelligence nowadays, we can see its applications in our real life. So now, for example, self-driving cars are becoming a reality thanks to artificial intelligence. So in cars can detect objects, can identify those objects, and it can ever estimate the speed of the vehicles. Also in the security field, so as we know, surveillance, for example, is a very difficult task, and sometimes it requires a big number of people. So artificial intelligence, it is making this task easier. So it can identify people, identify anomalies in crime scenes. So it's making this task easier. Also in the health field. So now, for example, from the retina image, you can identify the blood pressure, and you can doctors can predict cardiovascular problems such as heart attacks and strokes simply from those images. We have also GANs. So in GANs, we can generate example of image datasets. We can even generate photographs of human faces. So for example, let's go to this website here. In this website, it's just generating some images of people, and those images are not real, but they're just generated by GAN. Also, here in this website. Okay, here it will give you two photos. One photo is real photos, and the other it is generated by GAN. So we're going to play a game and to choose which photo is real. So I'm gonna say this one is real. Yeah, it's correct. So this photo is real, and this one is generated by GAN. Also, we can see also the applications of artificial intelligence in the art field. So now, artificial intelligence, and now thanks to artificial intelligence, we have a new type of champion. So thanks to the Google DeepMind algorithm AlphaGo, this algorithm was able to beat the world champion in the game Go, and it was the first algorithm to defeat a real world champion. Okay, so now we're going to go deeper into reinforcement learning. So, Ahmed?
Thank you, Sabrine. Okay, so earlier we presented the key elements in reinforcement learning. We defined what an agent is, what is an environment, what are the actions, what the state is, and the reward. And now we need a little bit of theory. So we will introduce a concept called Markov decision process. So a Markov decision process, or MDP, is a mathematical framework that allows us to formalize the reinforcement learning problem. So formally, an MDP is just a tuple composed of S, A, P, R, and gamma, where S represents all the possible states. A is a finite set of actions. P is a state transition probability. This probability characterizes how we transition from one state to the next, which means that it defines the probability that the agent will be in a state S prime, given that the agent is at the present at a state S and has performed an action A. R is a reward function. It is the function responsible for generating reward signals for the agent, and gamma is a discount factor that we will explain later on. Okay, next, yes. Okay, now let's visualize what an MDP can look like. So we can, for example, modelize the decisions taken by a student with a Markov decision process. So the student in this case is the agent, and the environment is the campus. So the student can interact with its environment by taking the actions shown in red, like it can study, it can sleep, he can go to the pub, maybe use Facebook or quit using Facebook. The circles represent the different possible states in which a student can find himself in. And there is a special state, the rectangular one, S5, and it represents a terminal state, which means that which means that we reached the end of the decision process. So every time the student takes an action and find himself in a new state, we call this a time step. So a time step is just an action that was performed by our agent, and the agent receives a reward and the next state. Okay, now let's take an example in this MDP. So let's say that the student woke up and found himself in the state S2. The Okay, now the student can either go to the class and study, or maybe use Facebook instead. Let's say he decided to study and he received a reward -2 and found himself in the state S3. Then the student maybe he decided to go to the next class and found himself in the state S4. And maybe at this point, the student felt tired and decided to go to the pub. And this short trip to the pub might have refreshed his mind, so he gets a reward of +1. Then this now we have the student at state S4 and decided to go to the pub, and now he can end up either in state S2, S3, or S4. The student cannot decide in which state he will end up, but rather the environment will put the student in one of these states. So there is 0 to probability that he will end up in S2, 0 for probability that he will end up in S3, and 0 for probability to end up in S4. So these probabilities are the state transition probabilities that we introduced earlier, and they define the randomness of the environment. Okay, let's say that after the student went to the pub, he decided to study, and he found, let's say that the environment had put the student in S4, so he decided to study and take his final class of the day. So he receives a reward of +10 and end up in a state S5, which is a terminal state that represents the end of the day. So this was an example of an MDP, and often reinforcement learning problems are formalized this way. Okay, so our goal in reinforcement learning is to maximize what we call a return. So the return GT is defined by this expression. It is basically the reward summed over all of the time steps infinitely into the future. And the way we control this return and make it finite is by using a discount factor gamma. Gamma is usually between 0 and 1, and it is used to make the return finite. It also determines how much the reinforcement learning agent cares about rewards in the distant future relative to those in the immediate future. So, for example, a discount factor equal to 0 means that the agent only cares about the immediate return, while a discount factor equal to 1 means that the agent cares equally about the immediate and the future rewards.
Okay, so thank you, Ahmed. So now we're going to talk about two different tasks of reinforcement learning. We have first the episodic task. So um, what is an episodic task? It is a complete sequence of interaction. So in those tasks, we have a starting point and finish point. So and those tasks can come to an end whenever the agent reaches the terminal state. An example of episodic tasks, for example, is the game of Super Mario. So, an episodic task began at the launch of a new Mario, and it will end when he will be killed, uh, or he will reach a new level. So, in reinforcement learning, when an episode will end, the agent will reborn in the same environment, but of course with the added knowledge of what happened in his past life. And we have also all continuous tasks. So those tasks are continue forever, so they have no terminal state. And as an example for continuous tasks, we can talk about an agent that do automated stock trading. So this agent will keep running until we decide to stop him.
Thank you, Sabrine. Okay, now we can talk about value functions, but first of all, we need to define very briefly what a policy is. So a policy is simply a distribution of actions given states. It is simply a mathematical way to define the behavior of an agent. So the policy simply tells what action the agent should take given that he is at a state S. And we want our agent to learn how to take actions that lead to the highest return possible. Next slide, please. Okay, so now we can introduce value functions. A value function is a function that attributes a value to each state. So we saw earlier how a student can end up in different states. Well, now we want to give a value to each of these states. This value describes how valuable it is to be at a given state S. So the value of a state S under a policy pi is by definition the amount of return that we expect to get by the end of the episode if we keep taking actions according to our policy pi or according to our agent. And similarly, an action value function Q is a function that evaluates how good it is to be at a state S and taking an action A. So now, instead of giving a value to each state, we are attributing a value to each pair of state action. Uh, So one might ask, why do we need to attribute a value to the states? Well, we will use this value in order to select the actions that will lead to the highest return. So for example, here we have a maze and we want our agent to escape this maze. The black rectangles are the states and the numbers represent the values of each state. So if we manage to accurately predict the value of each state, the agent can easily escape the maze just by going to the next state with the highest value of each step. And in a nutshell, finding the values of each state is one way to solve our Markov decision process, and hence build a good strategy capable of selecting smart actions. Okay, now we will introduce Bellman equations. So one might ask, how can we estimate the value of each state? Well, the good thing about the value functions V and Q that we introduced earlier is that they obey a recursive relationship. The state value function V can be decomposed into the immediate reward that the agent receives after performing an action, plus the discounted value of the successor states. Similarly, the action value function Q can be decomposed into the immediate reward plus the discounted value action of the successor states. So these two equations are called the Bellman expectation equations, and we can solve these equations in order to determine the value of each state. Solving these equations mathematically is very time consuming, especially for real reinforcement learning problems with millions of states. So there is a whole family of reinforcement learning algorithms called value-based methods that try to approximate the value functions, and these algorithms are fundamentally based on this recursive relationship in the Bellman equations. My colleague Sabrine will present a popular value-based algorithm called Q-learning that takes advantage of this recursive relationship in the Bellman equations in order to predict the value of each pair of action state in the MDPs.
Okay, so now, as Ahmed said, we were going to present our first algorithm for today, which is the Q-learning. So first we have this problem. So here we have a robot, and this robot has to cross this maze and reach the end. So, and of course, he will not have to step on those mines, and he will have to reach the end, crossing the shortest path possible. So for that, we at each step, the robot will lose 1 point because our goal is to encourage the robot to find the shortest path. Of course, when he will step on a mine, the robot will lose minus 100 points because and the game will end. And when he will get a power, he will get +1. And when the game will end, he will get +100. Okay. Now, how are we going to train our robot to reach the end goal with the shortest path and without stepping on a mine? For that, we're going to use the Q-learning algorithm. So we have here the QTable, and as we see here, for the lines, we have the different states, the start point, the nothing or blank square, the power square, the mines, and the end. And for the columns, we have the actions. So he's going to go up, left, right, or down. And the goal of this QTable is to calculate the maximum expected future rewards for each action and each step. So to make it simple, the table will guide us to the best action at each state. Now, how are we going to update the Q values at each in the Q table? So for that, we're going to use the following equation. So for each new Q value, as we see here, we have the state and the action. It will be the old value, so the old Q value at this state and this action. The learning rate, here we will have the reward that the agent will get if he's going to perform this action in this state. Here we have the discount factor. Here we have the maximum action that will give us the, so for by that we want to say that we want to see which action is going to give us the maximum Q value for the new state. And for here we have the old Q value at this state and this action. So we're going to update the values of this Q table at each new state using this equation. So how the Q learning algorithm will work? So first we're going to initialize the Q table. All the values were going to be on 0. Then the agent will choose an action. So, and then he will going to perform the action in the environment. He will get a new state, and of course he will measure the reward, and then he will update the Q table with the equation I've showed you in the last slide, and he will repeat the iterations. He will finish those iterations when he will lose the game. For example, for the main example, if he will step on a mine, or when he will reach the ending point. And of course, after a lot of iterations, we will have a good Q table. But the question now, how is the agent is going to choose the actions? As we said at the initial state, all the Q values will be set on 0. So how the agent will choose those actions? So That's why we're going to talk now about the exploration and the exploitation trade-off. So, at the beginning, the agent should explore the environment to improve his knowledge. So, and by exploring his environment, we mean that at the beginning, the agent should choose random actions. And then at each step, the agent will have two choices. He should either take the best action based on the known information. So here in the Q learning algorithm, the known information is the information in the Q table, or he should try to find more information about the environment in order to improve his knowledge and to discover a way to obtain better rewards in the future. And the way we do it, so we have an epsilon value, and if with a probability 1 minus epsilon, the agent will choose to perform the action with the maximum Q value, and with probability of epsilon, he will choose to perform a random action. But how are we going to choose this value of epsilon that will help the agent to explore and do the exploitation in the environment? So, at the beginning, as we said, the agent knows nothing about the environment, so he really should do a lot of exploration and to choose too much random actions in order to explore the environment. But then, sorry, but then he will be more comfortable about the values on the QTable, and he will not really need to do a lot of exploration, but he will know a lot about his environment, and at the end of the training, the agent really must do only exploitation. So as we see here, at the beginning, the epsilon rate must be really high, but at the end of the training, it should increase, and then at the end, it should reach a very small value. So he will do only exploitation, and he will only get the information based on the Q value. And at the beginning, we generally put this value to 1, so he will only choose random actions. Then we will increase this epsilon rate until reaching a really small value. Okay, so now we're going to try to do a little application of what we've learned with in the previous slides of Q learning. So we're going to use Google Collab here. So you have to connect to Google Collab. So here I am in Google Collab. Here you will go to GitHub. You will enter my username, and then you will use the AL workshop, and you will find here the notebook of the Q learning. Okay, so here we're going to choose to work with a gym environment. The gym environments were made to test different reinforcement learning algorithms, and today we're going to test our Q learning algorithm with one of those environments, which is the frozen lake environment. So, Ahmed, the floor is yours.
Okay, thank you, Sabrine. So today we decided to use the frozen lake environment. So the GYM library is a reinforcement learning library that contains a lot of environments. So we're going to use it today. So the frozen lake problem can be described as follows. So there is a frozen lake and the water is mostly frozen everywhere, but there are few holes inside this lake uh, where the ice has melted. So, for example, here you can see a representation of the surface of the lake. So there is we can represent the lake as a grid, a 4x4 grid, and there are 16 possible states. The first one is the start state. It is the state in which our agent will start in. Then there are other states like the F. F means that the water is frozen, so our agent can walk on it. And there are other states called H, which represent a hole. So our agent will try to reach its goal. Uh, it is represented by the letter G. And the problem is that the floor can be slippery. So when the agent performs an action, let's say he decides to go down, he will not always find himself in the state below because the floor is slippery. So there is some randomness in the environment, and it's up to the agent to figure out how to get out of this maze. Can you go down a little bit, Sabrine? Okay, so we said we were going to use the gym library. So we import this library by executing the first cell, and we also need NumPy. And in order to create the environment, we just have to call the gym.make, and we input the name of the environment that we are going to work with today. So we just create a new environment with the second cell. And once we create this environment, we can explore it by typing print environment.actionSpace in order to see the possible actions that the agent can take. And also we can observe the observations that are given, that the environment gives back to the agent. So by calling environment.observation_space. So in this case, since we are working in a grid, in a 4x4 grid, there are 16 possible states and thus 16 possible observations for the agent.
Okay. Yes. Yes. So thanks, Ahmed, for presenting the different characteristics of our environment. So we're going to now to implement our Q-learning algorithm. So first, we're going to start by importing the different hyperparameters. So first, we have the epsilon that I've already presented in the previous slides. We have also the minimum epsilon value. So we put to the agent the minimum epsilon value that he will reach. So as I've said before, we will reduce this value of epsilon, and this is the minimum value that the agent can reach. We have also the decay rate, the rate by which we decrease the epsilon. Of course, here we're talking about an episodic task. So, and we're going to train our agent for different episodes. And here we've chosen to train him for 100,000 episodes. For the maximum number of steps in one episode, we will give to the value of 100 to this hyperparameter. And of course, here the learning rate for the Q-learning algorithm and the discount factor. Okay, so the first thing that we're going to do is to construct our QTable, and so the size of the QTables, as I've said, the number of lines are the number of states, and the number of rows are the number of actions. And as initial values, we will put all the values to 0. Then we were going to implement different functions that we're going to need later for our algorithm. So here, the agent, this function will help the agent to choose the action according to the state. So as we see here, according to the value of epsilon, he will choose to perform a random action by sampling an action from the action space, or he will choose to take an action from the Q table. So he will choose the action that will give us the maximum Q value from the Q table. So here he's going to do an exploration, and here he's going to do exploitation. Then in this second function learn, so for the agent, he will learn to update the Q values in the Q table. So he will have the current observation and the next observation, and he will have to update the Q table using the following equation that I've already mentioned in the slides. And now the agent will start to learn and to do the training using the Q learning algorithm. So of course here the env reset will give us the initial state for the environment, and then for each step, the action, the agent will choose which action he's going to perform. Then he will send this action to the environment, to the gym environment, and this gym environment will send him back the new state, the reward, whether it is done or not. And we mean by done either we want to say if the agent is in his final state or not. And of course here the agent will learn, and he will update the different Q values in the Q table. And then if done, so if the reward is 0, it means that because here when he is in bad locations, he will get -1 or -10. So if the reward is higher than 0, it means that the agent is winning this episode, and else it means that he's losing this episode. And here, after launching this run, we can see here the results of the different episodes. At the beginning, the agent has he's losing a lot of games, and then at the end we can see that now he is learning from his environment, and he is winning more than losing. So we may the meaning of that is that the agent is now capable of performing good actions in his environment. Ahmed, do you want to add something?
No, thank you, Sabrine. And please, if you have any questions, You can ask us in the comments. And thank you for your attention.
Yes, thank you.
Thanks so much, guys, for the talk. Are there any questions? Don't be shy. In any case, if you do have questions, you can add us at GDG Carthage on Twitter, or you can leave a comment in the comment section on Facebook, or you can just directly let Sabrine know. She's on Twitter at Sabrine with 2 eyes 28. And if anyone has any questions, you can also DM me or at me. I am Zahra, so Zazu, Zazouws. Ahmed says, thanks a lot. Thank you for watching, Ahmed. If anyone has any other questions, please let us know. Thank you so much for following our feed and for following this talk. Sabrine and Ahmed, do you guys have any final recommendations or tips for people?
Okay, that was just an initiation for reinforcement learning, but really advise you to study more about this field because it's really interesting.
Ahmed?
Yes, as Sabrine said, it is really a promising field, and yes, it's an interesting field. I encourage you to explore it. And if you have any questions, you can contact me on my email. And thank you.
Awesome. Thanks very much, everyone, for watching. Stay with GDG Carthage as we have, if I'm not mistaken, a couple of other talks today in a little bit, not right now, right now. Let me just check. So the next talk is actually in 6 minutes, actually, with Khal Batish and Muwafaq Ayedi on GCP workshop for AI and big data. Follow our channel on YouTube to get notifications on when we are live. Thank you very much. Have an excellent day. And thank you for being with us during this DevFest. Thank you, everyone.